Students, now we'll discuss about open pipe. How can we generate the stationary waves in an open pipe, and what is the behavior of the particles in an open pipe with respect to the frequency of the sound waves by which these stationary waves will be generated. Okay. Now first of all, we will discuss about the open pipe. What is open pipe? A pipe or tube with both ends open is called the open pipe. Okay. And for the loud sound, it is necessary the antinode will be formed at the open ends for maximum or loud sound. Antinode must be formed at open ends. Okay, beta. Now we'll discuss about the frequency change. When we change the frequency of the waves by which we are generating the stationary waves in the open pipe, so what will be the behavior of the speed and the wavelength along the length of the tube? So for first harmonic, what is the meaning of first harmonic? When we heard a frequency at which we can heard the first loud sound, the first harmonic. For the minimum frequency, when we heard the loud sound, it is necessary the antinode is formed at the open end. It is the middle point of the tube. That will be the condition when we heard the first loud sound for the minimum frequency. That means it is antinodal position, it is node position, and it is node position. When the frequency is minimum, the wavelength will be maximum because of the inverse relation between the frequency and the wavelength. Now we can say that the complete length of the tube is converted into half of the wavelength, because if you observe here, this part is equals to the half of the loop and this part is also equals to the half of the loop. So half loop plus half loop is equals to one loop, and we know that the wavelength corresponding to the one loop will be half of the lambda. So we can write here the L is equals to lambda over 2, and we can show the lambda in terms of the length of the tube, that will be 2 times of the length. It is the maximum wavelength generated in this condition when we heard the first sound. Now to calculate the frequency, we will use the wave equation, that is V is equals to F lambda, and frequency becomes now V over lambda. Now we can substitute value of the lambda here, that is 2L. Because it is the first loud sound and it is the first harmonic, and this frequency is the minimum frequency, that is called the fundamental frequency. So we can show it by F naught, that is the minimum frequency. So it is called the fundamental frequency. Because we cannot heard a loud sound for the less value of this fundamental frequency. Okay, students? So that's why it is called the fundamental frequency, and the other harmonical frequencies will be the integral multiple of this fundamental frequency. Now we'll discuss about the second harmonic. For second harmonic, And this second harmonic is also known as the first overtone. Basically, it is the second loud sound can be heard by the observer it will be the condition of the stationary waves in which we can heard the second loud sound for the second harmonic, because we have in the middle position the antinode, it is the node, it is also the node, and at the open ends we will get the antinodes. So for this condition, now we will relate the length of the tube with the wavelength generated. Okay students, now we can observe here from this point to this point, that means it is a half loop and it is a complete one loop and it is also the half loop. So half loop plus half loop becomes one loop, and one loop plus one loop is equals to two loops. And we know that the wavelength corresponding to the two loops is equals to the 1 lambda. I can show you this resemblance with the loops generated in the result of the stationary waves in the string. Just like it is a node position, it is the antinode position, it is the node, it is antinode, node and antinode, node, antinode, node and antinode. Now if we start from here, because at both ends we will get the antinodes, so it means that we are starting from this position, so we will remove this position. Okay, we are starting from this position, and the first loud sound will be heard for this position, and the second loud sound can be heard for this alternate antinode. So if you observe the wavelength, it is completed one wave here, so that's why we can say that this distance is 1 lambda. So we can write here the L is equals to the 1 lambda. Now to calculate the frequency, we will use here the wave equation, that is V is equals to F lambda, and frequency is equals to V over lambda and V upon L. Now because we are talking about the second harmonic and the fundamental frequency is denoted by F naught, so we can use here the subscript 1 to show the first harmonic. Because it is the first harmonic, it is a zero harmonic. Now we are using the subscript to show the number of overtones in this condition. So 0 means zero overtone, 1 means first overtone. Now we'll show this second harmonic frequency in terms of the fundamental frequency. So we have 2 here in the denominator, so we will multiply the numerator and denominator by 2. So it becomes now the F1 is equals to 2 times of V divided by 2L, and we also know that the 2 times of V over 2L. So this second harmonic frequency can be written as in terms of the 2 times of the fundamental frequency. Now we'll discuss about the third harmonic.